Mr. A.
Oh, hey, Misty. What's up?
You know what? I was thinking, what's your favorite kind of tree?
Oh, wow. If I had to say that, I'd probably say it's my family tree. I think it's very rich and has a vibrant and interesting history. Why? What's your favorite kind of tree?
Man, good question. I would have to say it's Trigonometry!
Well, I'm glad I asked. And if you really like trigonometry, you should check out these two cool triangles.
Cool.
Yeah, that's what I said. They're also triangles. So they're pretty interesting. And what you in the audience might notice, and you of course as well, Miss T, is that they are similar triangles. We can tell because they've got the same angle measures, a 30, a 90, and then this third angle must be also same. And then they've also got a proportionality. Because they're similar, one is a scaled version of the other. If we take this and multiply by 2, we're here. If we take this and multiply by 2, we're over there. So one is a scaled version of the other. And in my opinion, that's fairly interesting. And what's really cool about similar triangles is that because of that constant proportionality, there's always a constant ratio between sides. So if we look at the ratio between side A and side C, in the first case it's 1.5 over 3, which is 1/2. And over here, A over C is 3 over 6, which is also 1 over 2. So in both cases, they maintain that proportionality. And what we're going to be looking at today is how that proportionality kind of works with all triangles. We're going to see how angles and sides are related in right triangles. And when we perform computations, we're only going to work with one angle at a time. So we're always going to talk about things from the perspective of one particular angle that we'll choose. And we'll label it somehow. If it's already labeled, super duper. If it's not, then we can usually use the Greek letter theta, which is like 0 wearing a belt. And we'll always label the sides of the triangle based on whichever angle we are using.
All right, so we're going to look at some definitions here. I'm going to just chat about them and move right on. So if you need to, pause the video, write these down. But when we're talking about a particular angle or theta of a right triangle, we can define the following terms. So we have something called the hypotenuse. And the hypotenuse is always going to be the longest side of a right triangle, right? Right. That side length is always opposite the 90-degree angle. So if we're looking at a triangle, boop, 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 my hypotenuse is always going to be opposite my 90-degree angle there. My opposite side is, of course, going to be across from my chosen angle. And when I talk about chosen angle, my chosen angle can vary from question to question or triangle to triangle. So we will have our opposite side also vary in respect to it. So the opposite side is not an arm of that particular angle. It is the only one not directly attached as opposite. Whereas the adjacent side is the side next to the chosen angle. But when we're looking at any particular angle, it's next to two sides. One of those sides will always be the hypotenuse. So it's the side next to the chosen angle that is not the hypotenuse. And let's take a look over here. So we're going to look at some examples, and it says label the opposite, adjacent, and hypotenuse for each triangle based on the indicated angle theta. So, get my yellow highlighter here. This guy here is theta. So this, in my case, is going to be my chosen angle. Now, when I'm labeling my triangle, I always start with the hypotenuse. A, because it's always consistently the same thing regardless of what triangle you have. And B, it's, in my opinion, the easiest one to find because it's the longest. So this one here is going to be my hypotenuse. It is also directly opposite my 90-degree angle. So that's uber nice. Now the other two. One has to be opposite, one has to be adjacent. If I am looking in my particular angle, these two pink lines that I'm drawing are the arms of my angle, right? If I'm talking about my opposite side, it is not one of those two arms. It is across from that particular angle. It is not touching it in any way. My adjacent would then be one angle that is one side length that's directly next to my angle, but is not the hypotenuse. So looking at those two pink sides, we already know one is the hypotenuse. That means this guy over here, that's my adjacent. So we could label them accordingly. I'd like you to pause the video, test the next two out, then pause and return, and we're going to go a little bit quicker this time. So, here we have my angle theta. I'm going to start by labeling my hypotenuse. It is the longest side and is directly opposite my 90-degree angle. Next, here I have my angle theta, and I want to label my opposite. My opposite side is the one that is directly across from it. It is not touching that angle in any way. And my adjacent is directly next to my angle in question, and it is not the hypotenuse. Last but not least, we have my angle theta over here. My hypotenuse, I'm always going to start off with that. It's personal preference. You do you. But it's directly across from my 90-degree angle. It's also the largest or longest side of my triangle. Next, I'd like to do my opposite. My opposite is directly across from my angle theta. It is not touching it in any way. And my adjacent is my last side. It is directly next to my angle. It is not my hypotenuse. So hopefully you feel pretty confident doing that.
Because we are going to use those sides to find out some information about triangles. So we're using three primary trigonometric ratios. One is called the sine ratio. That's abbreviated. You might see it on your calculator. Like, why does my calculator say sin? Because I would do anything but. There's also the cosine ratio, which is shortened to cos. And then the tangent ratio, which is shortened to tan. And they're defined in a very particular way. So the sine of an angle, theta, is defined as being the ratio between the opposite side and the hypotenuse. The cosine of an angle is defined as being the ratio between the adjacent side and the hypotenuse. And there's one last combo we don't have yet here, and that's involving tan theta. We've talked about the opposite hypotenuse, the adjacent hypotenuse. What we haven't talked about is the ratio between the opposite side and the adjacent side. That's how those are defined. And sometimes you might say, like, sine theta is opposite over hypotenuse for short form, or cos theta adjacent over hypotenuse, or tan theta being opposite over adjacent, just to use that O and H and A as we used when we were labeling these triangles. Now, it seems like a lot. That's a doozy to memorize. But you can use this helpful mnemonic called SOHCAHTOA. You see, SOHCAHTOA was an ancient philosopher who believed in trigonometry. Just kidding. What this tells us is that the sine of an angle is opposite over hypotenuse, that the cosine of an angle is adjacent over hypotenuse, and that the tangent of an angle is opposite over adjacent. I'll tell you, I wrote this on pretty much all of my trig quizzes and tests when I was first learning this stuff, and you can too. SOHCAHTOA is extremely helpful.
So, when we see a statement such as like sine of 30 degrees is equal to 0.5, what does that actually mean?
I don't know.
Well, that means that in a right triangle, with a 30-degree angle, the ratio between the opposite side length and the hypotenuse is 0.5 or 1/2. So let's write that down. In a right triangle with a 30-degree angle, the ratio between the opposite side and the hypotenuse hypotenuse is 0.5 or 1/2, because 0.5 and 1/2 are same.
And it's very key that this is in a right triangle. So we are only working with right triangles for our business this year. And you might see stuff with other triangles next year, but for us, right triangles only.
And SOHCAHTOA only works for right triangles. So if we had an equilateral triangle,
Sure. Yeah.
or an isosceles triangle that didn't have a 90-degree angle present, then we would not be able to use SOHCAHTOA. So it's very important, like Mr. A said, that it is in a right triangle. All right, so we're going to take a look at these last two examples, but before we do, there's a couple of big no-nos that I want to draw your attention to. Okay, note that when we're talking about sine, cosine, or tangent, these are functions. So they themselves are a function on a particular value. Kind of like if I had a plus sign, a minus sign, a multiplication sign, or a division sign, they can't be written in isolation. I can't write division equals 4. In the same way, I can't write sine is equal to some number, because it's saying a function is equal to something. But a function without an input means nothing to me. So I will never write sine is equal to some sort of angle or sine is equal to some sort of number, because that would be, well, let me find red. That would be bad, right? That would be the same thing as saying, like, well, my multiplication sign is -7. Well, that kind of looks like an X, so I guess that's a little hard to say. But I wouldn't say, like, minus is equal to -7, right? So when we're writing these things, we need to make sure our sine, cosine, or tangent have an input next to them. So we could say the sine of angle 25 degrees. Or if we don't know our angle, we could say the sine of angle A. We could say the cosine of theta is equal to something, let's say 1/2. Right? We can say those statements as long as there's an input value present. Okay? These are big common mistakes that happen, but hopefully you will avoid them because they are so wrong. All right. Now, what we're going to do in this next question, or this last, I guess, set of questions, is we're going to determine what sine of theta, cosine of theta, and tan of theta are for each of the triangles. We are going to express our answers as fractions. We're not going to convert to decimals. But we're going to make sure that those fractions are fully simplified. Okay. So when I'm looking at a question like this, I'm kind of starting off the same way I did when I was labeling my triangles. I want to make sure I know what angle I'm talking about, and here it's labeled angle theta. I'm going to go back to my colors of joy, like purple. And I'm going to start off just by labeling the opposite, adjacent, and hypotenuse, just for us to clearly see that. Remember that our hypotenuse is always going to be that longest side, which is always directly across from our 90-degree angle. Our opposite will be directly across from our angle itself, and it won't be touching the angle in any way. And our adjacent is right next to our angle that's not the hypotenuse. All right. So according to SOHCAHTOA, I know that sine of theta is equal to my opposite over my hypotenuse. Well, in this case, I know that sine of theta, my opposite is 8, my hypotenuse is 17. So I could say sine of theta is 8 over 17. That can't be reduced because 8 and 17 don't have any common factors. So we move on. Next, we have my cos of theta. We have ka in SOHCAHTOA is adjacent over hypotenuse. And we have my adjacent in this case being 15, my hypotenuse being 17. And last but not least, we have my tan of theta is toa, so opposite over adjacent. So tan of theta in this case, opposite is 8, adjacent is 15. And just to be super clear of what my final answer is, I'm going to box them all and call it a day. Well, it's kind of a wonky eye.
That's okay. We love it all the same. Try the next one if you dare. and I'm sure you do dare, so dare. I'm going to, of course, jump right in here. There's my angle. So my hypotenuse is over there, across from my 90-degree angle. My opposite side is across from theta, which leaves just this one side as my adjacent side. And now I can go with my definitions. Word on the street is that sine of theta is opposite over hypotenuse, which means that sine of theta must be 12 over 15. Done, right?
No!
Ah! What did I miss?
Oh, you could reduce 12 over 15.
Oh, snap. You're right. I don't want to get that E1 communication error for having an unreduced fraction in my final answer. Now I get it. So I should reduce that to 4 over 5. So that's sine of theta. And then, of course, we're asked for the other two as well. So let's get cosine of theta, which, as I've heard, is adjacent over hypotenuse. So in this case, cosine of theta is 9 over 15. And I learned my lesson from last time. I'm not done this yet. I need to reduce that fraction. So 9 over 15 is something like 3 over 5. And I'll put a box around that eventually. Tan theta is opposite over adjacent, which for this particular case is 12 over 9. And just reducing that, we get 4 over 3. Note that we did not say something like tan is 4 over 3. That goes on what Ms. T was saying up here, is that there always needs to be some sort of argument in there. You can't say tan equals, but we can say that tan of an angle equals. If you don't do that, that's an E13 communication error, where you omit the variable in a trig function. Is bad.
It's really bad.
Yeah, it's practically the worst. What color did I use to circle it? I mean, I circle with boxes. That's how circles work. And that's that example done. If you got all those answers on your own, you should give yourself a high five. And I did, so rock solid.
There are some questions in the textbook. There's actually only one question. It'll ask you to write out the tan ratio, but also write out the sine and cosine ratio just for some practice. That is it. That is all for us today, and we will see you next lesson.
Until the future, goodbye.